In this section, we're going to be going over how to solve compound probability, and these are going to be problems that contain the words and or. And we're going to do this without constructing a sample space. Okay, so let's start with the or problems. So the or probability requires obtaining a successful outcome for at least one of the given events. So if you see the word or, it's going to mean the probability of at least one of the events. And the formula we use is called the addition formula. And it is the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B occurring at the same time. So let's see kind of why this formula is the way it is. So thinking in terms of sets with a Venn diagram, we know that A or B is going to be everything shaded in circles A and B. And we know that in order to obtain this, it probably makes sense to add A and B together. So we know that set A would just be all of circle A. We know that set B would be all of circle B. So the issue with adding these together is that we actually add that middle portion twice. We added the overlap twice when we should only be adding it once. So we need to subtract it off. And subtracting off the overlap is A and B. So that's why the formula is probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So let's do some examples here, starting with this first one. Suppose that we roll one die, determine the probability of rolling an even number or a number greater than 4. So we see the or here. So we know that we're going to be using this formula. So I'm going to let these two events be event E, which is rolling an even, event G, which is rolling a number greater than 4. So our formula here is going to be probability of E or G. So same formula as the last page, except I'm just using E and G instead of A and B. It's going to equal the probability of E plus the probability of G minus the probability of E and G. So let's figure out each one individually and then add up the result. So the probability of rolling an even number, there are going to be 3 even numbers. There's going to be 2, 4, and 6. So that's going to be 3 possible outcomes out of 6 total outcomes because we're rolling a die. And for the next one, the probability of rolling a number greater than 4. So greater than 4 is just going to be 5 and 6. That's going to be 2 total outcomes out of 6 possible outcomes minus the probability of E and G. So that's going to be the probability of E and G. E and G is going to be rolling an even that is greater than 4. So it has to be both even and greater than 4. The only number that's going to be even and greater than 4 here is going to be 6. So that's going to be 1 outcome divided by 6 total. So once we have these, we can just add them all up. And since the denominators are the same, all we have to do is add and subtract the numerators. So it's going to be 3 plus 2, which is 5, minus 1, which gives us 4. So this is going to end up being 4 out of 6, or we can simplify that to 2/3 by dividing the numerator and denominator by a common factor of 2. So this is about 0.67 as a decimal. Let's do a couple other examples here. For the next one, each of the numbers 1 through 10 is written on a separate piece of paper. The 10 pieces of paper are going to be placed in a hat, and 1 piece is randomly selected. We want to determine the probability that the piece of paper selected contains an even number or a number greater than 6. So pretty similar to what we just did. So let's let event E be an even number, and let's let event G be a number greater than 6. So we're going to have our formula, same formula as before. And let's figure out these individual probabilities and then add them on up. So for the probability of E, For an even number, that's going to be 2, 4, 6, 8, or 10. That's going to be 5 possible outcomes out of 10 total outcomes. And next, for a number greater than 6, that's going to be 7, 8, 9, 10. That's 4 total outcomes out of 10 total outcomes. And next, we have to subtract off what they have in common. So we need a number, an even number that is greater than 6. So an even number greater than 6 is going to be 8 and 10. That's going to be 2 outcomes. So that's going to be minus 2 over 10. 5 plus 4 is 9, minus 2 is 7. That gives us a probability of 7 over 10. And that brings us to our definition of mutually exclusive. So we say that two events A and B are mutually exclusive if it is impossible for both events to occur simultaneously. So if events A and B are mutually exclusive, what this means, since they can't occur at the same time, that means the probability of A and B both happening is going to be 0. So that means the addition formula ends up simplifying to the probability of A or B equals the probability of A plus the probability of B. So let's go ahead and see an example. So a similar example to what we just had. The numbers 1 through 10 are written on a separate piece of paper. The 10 pieces of paper are placed in a hat and one is randomly selected. Determine the probability that the piece of paper selected contains a number less than 5 or a number greater than 8. So I'm going to let L be the event that it's less than 5 and G be the event that it is greater than 8. And writing down our formula here, we have our addition formula, so let's figure out these probabilities. So the probability of L, the probability that it's less than 5, if it's less than 5, it can be 1, 2, 3, or 4. That is going to give us 4 possible outcomes out of 10 total outcomes. The probability of G greater than 8, that's going to be 10 or 9. That's going to be 2 outcomes out of 10. Minus the probability that they have in common. So we need a number that is greater than 8 and less than 5. So there's no number that's going to be less than 5 and greater than 8. So this is going to actually be 0. And that is because these are mutually exclusive events. So let's go ahead and finish it up. Now we have 4 plus 2, we get 6. That gives us 6 out of 10, and that simplifies. We can divide by a common factor of 2, and we get 3 over 5 as our probability. Let's do one more set of examples before we move on to the last thing. We are going to select one card from a standard deck of playing cards. We want to determine the probability of A or B for each of the following. So for the first one, A is going to be the event that it is an ace, and B is the event that it is a 9. So we have our addition formula here, and we want the probability of A. The probability of A is the probability that it is an ace. There are 4 aces in the deck, 52 cards total, so 4 out of 52. Plus the probability that it is a 9. There are 4 9s in the deck, 1 for each suit, once again, 52 total cards, minus the probability that it is an ace and a 9. So these events are mutually exclusive. It cannot be an ace and a 9, so that's going to be 0. So 4 plus 4, we get 8 divided by 52, so we get 8 over 52. And this actually ends up simplifying to 2 over 13 after we divide by a common factor of 4. Okay, and then the next one here, the event A is going to be that it's an ace, event B is that it is a heart, and we're looking for the probability of A or B. So we write down our formula and do what we just did. So the probability that it is an ace is going to be, once again, 4 out of 52. The probability that it is a heart. So a heart is one of the suits. Each suit has 13 cards. That's going to be 13 out of 52 minus the probability that it is a heart and an ace. There is one card that's a heart and an ace, and that's the ace of hearts. So that's going to be 1 out of 52. So we go ahead and add up. 4 plus 13 is 17, minus 1 is 16. 16 out of 52, and that ends up simplifying by a factor of 4. We get 4 over 13 as our probability. Just keep in mind you can also be writing these answers as decimals. Next one, we have A is a red card and B is a black card. And we want the probability of A or B. So the probability of A, the probability that it is a red card, there are 26 red cards out of 52 total. So the red cards are going to be the diamonds and the hearts. The black cards are going to be the clubs and the spades. So there are 26 black cards out of 52 total, minus a card that is both black and red. No cards are both black and red. These are mutually exclusive, so that probability is going to be 0. So adding these up, we get 52 over 52, which ends up just being 1. So since that's 1, that means it must happen. That's because all cards, all the 52 cards are either red or they are black. Okay, and then the last one here, we have A is a face card, B is a red card. So we want the probability of A or B. So for the probability of A, the probability of a face card, so this one's a little bit more difficult. The probability of a face card, there are 3 face cards for every suit. There are 4 suits. 3 times 4 gives us 12. So remember, a face card is a jack, queen, or king, and there's 3 per suit. So that's going to be 12 over 52 plus the probability of a red card. We already said there's 26 red cards, so that's going to be 26 out of 52, minus the probability that it is a face card and a red card. So there's actually going to be 6 red cards that are face cards, and that's going to be the jack, king, and queen from the suits of diamonds and hearts. So once we have that, go ahead and add them on up. 12 plus 26 gives us 38, minus 6 gives us 32. 32 over 52, divide by a common factor of 4, and that's going to give us 8 over 13 for our probability. So an 8 in 13 chance of pulling out a face card or a red card. So for the next thing now, this brings us to AND problems. We just did OR problems. This is going to be AND problems. So the AND probability requires us to find the probability when events happen in a sequence, so one after another. So that's going to be event A occurring and then event B occurring. So to determine the probability of A and B, we're going to use this formula, which is called the multiplication formula. The probability of A and B equals the probability of A times the probability of B. So this is very similar to the counting principle that we did previously. And also take note here that probability of A and B, this is not the same probability of A and B that is in the addition formula that we just did. It's written exactly the same, but it's something completely different. In the addition formula, the probability of A and B is those events occurring simultaneously. This time it's one after another. So this AND can be thought of as and then. So it's in a sequence. Okay, so let's do some examples. The first one is 2 cards are selected with replacement from a deck of cards. Determine the probability that 2 spades are selected. So I'm going to let the event A be the first one is a spade, and then event B is the second one is a spade. Okay, so we want the probability. We want the probability of A and B. This is going to be the probability of A times the probability of B. So the probability of selecting a spade for the first one, probability of A, there's 13 spades out of 52 total cards. So there's 13 spades because each suit has 13 cards, times the probability of selecting a spade again. So the key phrase here is with replacement. We took out the spade and then we randomly put it back in the deck. So there's still 52 cards total and there's still 13 spades. So it's still 13 out of 52. So when you multiply these, it's going to be in your interest to reduce them first. 13 out of 52 reduces to 1 over 4. So it's 1/4 times 1/4. That's going to give us 1/16. And we have to remember that when we multiply fractions, we don't need common denominators. We multiply straight across. 1 times 1 is 1. 4 times 4 is 16. Okay, so let's do a question that looks pretty identical. We have 2 cards are selected without replacement from a deck of cards. Determine the probability that two spades will be selected. So once again, it's going to be the event A is going to be that the first is a spade. Event B is going to be that the second is a spade. And we want the probability of A and B. So the probability that the first one is a spade is just 13 out of 52, same as what we just did, 13 spades out of 52 total cards, times the second one is a spade. So this time it's without replacement. So we took out a spade and we did not put it back. That means there's going to be 12 spades left out of 51 total cards left. So this time we had to subtract 1 from the numerator and denominator. And we can simplify this first. It's going to be 1/4. We can simplify 13 over 52 to 1/4. 12 over 51 simplifies to 4 over 17 if we divide by 3 in the numerator and denominator. And if we multiply straight across here, the 4's will actually end up canceling. 4 divided by 4 is 1. We end up getting 1 over 17 as our probability. So that's the probability of selecting it without replacement. We saw that with replacement, it was 1 over 16. So with replacement was a little bit better. And for this last thing here, we have independent events. So event A and event B are independent if the occurrence of one of them does not affect the occurrence of the other one. And then conversely, 2 events are dependent events if the occurrence of one of them does affect the occurrence of the other one. So something that we've already done is experiments with replacement or without replacement. Experiments done with replacement are independent events. Experiments done without replacement are dependent events. So the one without replacement that we just did, we saw that the sample space changed from 52 to 51, and so did actually the number of spades in there. So that changes the second probability, so that means they're dependent. So let's see an example here. So 100 people attended a charity benefit to raise money for cancer research. 3 people in attendance will be selected at random without replacement, and each will be awarded 1 door prize. We want to know, are the events of selecting the 3 people who are awarded the door prize independent or dependent? So the answer to this is that these are going to be dependent events because it's done without replacement. So without replacement, so that means for this case, each time a person is selected, it's going to change the probability of the next person being selected. Okay, let's do one more example here. So a new medicine was given to a sample of 25 of Dr. Cleary's patients with flu symptoms. Of the total, 19 patients reacted favorably, 2 reacted unfavorably, and 4 were unaffected. 3 of these patients are selected at random. Determine the probability of each of the following. So the first one, let's determine the probability that all 3 reacted favorably. Okay, so I'm just going to label favorably as event F, unfavorably as event U, and unaffected I'll put event A. Okay, so the probability that all 3 reacted favorably, this is actually going to be the multiplication rule. It's going to equal the probability that the first one reacted favorably times the probability that the second one reacted favorably times the probability that the third one also reacted favorably. Okay, so this time we have 3 different people to worry about in this case. So the probability that they react favorably, so this is going to be empirical probability because we actually have an experiment being done. We have some data. Favorably is going to be 19 out of 25 because 19 out of the 25 reacted favorably. And we have to take into consideration that the first one reacted favorably. That means there's only 18 left to choose from. And since we took one out, that means there's 24 total left to choose from. For the last one, it's going to be pretty similar to what we just did. Since we took 2 out, there's going to be 17 favorables left, and then 23 total patients left. So you can see how we're just subtracting 1 in the numerator and denominator here. So when we multiply this straight across, we're going to get 969 divided by 2,300 as our probability. Okay, let's see this next one. We want the probability that the first patient reacts favorably, the second one reacts unfavorably, and the third patient is unaffected. So that's going to be the probability of F, that they reacted favorably, times the probability of U, that they reacted unfavorably, times the probability of A, that they were unaffected. So the probability that they reacted favorably, we said that was 19 out of 25, times the probability they reacted unfavorably. 2 of them reacted unfavorably, so that's going to be 2 out of, now we only have 24 left. So from the favorably one, we took 1 out of the sample space, so 1 from 25 to 24. For unaffected, there are 4 that were unaffected, so that's going to be 4 out of, now there are only 23 left because we took out 1 from the favorable, 1 from reacting favorably, 1 from unfavorably, so now we have 23 left. And now we're going to multiply all of these together, and it ends up simplifying, so I'm just going to simplify it in one sweep here, to 1,725. Or once again, you can multiply it. Kind of might be a little bit difficult to recognize how to simplify it at first. There's a way that you can simplify it before multiplying. You can recognize that we can actually simplify 2 over 24. We can simplify that first, and that'll give us 1 over 12. And then you can simplify the 4 with the 1 over 12 if you want and get 1 over 3. Okay, so for the next one, we have the probability that no patient reacted favorably. So this is going to be a little bit trickier. It's going to be the probability that the first did not react favorably times the probability that the second did not react favorably times the probability that the third did not react favorably. So not favorably, it doesn't mean unfavorably, it means just not favorably. So it takes into consideration unfavorably and unaffected. Or unaffected, I guess I should say. So 19 reacted favorably out of 25. So the ones that the ones that did not react favorably are going to be 6 out of 25. It's going to be 25 minus 19. It's going to be the other 6, which does take into account unfavorably and the unaffected. Okay, so first not favorably is going to be 6 out of 25 times the second unfavorably is going to be 5 out of 24 because we have to subtract 1 from both of those, and times the third not favorably, 4 out of 23. Once again, subtract 1 from both of those. So multiplying straight across here, this ends up simplifying to 1 over 115. Okay, and for the last one, we want the probability of at least one patient reacting favorably. So this could be one patient reacting favorably, 2 patients reacting favorably, or 3 patients reacting favorably. We have to remember that the probability of at least one, we can use a little shortcut. The probability of at least one is 1 minus the probability of none in this case. And the reason why this is a nice shortcut is because we just calculated the probability for none favorably, and we got 1 over 115. So our answer is 1 minus 1 over 115. And we would have to get common denominators here of 115. The 1 becomes 115 over 115 minus 1 over 115. We end up getting 114 over 115. So the probability of at least one reacting favorably is pretty high. 114 divided by 115 is a pretty high probability. Okay, so that is it for this section.